All right, for step 3, our calculation stage, we are back down to just having a limited number of formulas to deal with. So we're done with crazy ANOVAs with 9 and 13 calculations. We've only got 4 things here. And 2 of the 4 are literally repeats from all the way back in chapter 4. One of them is a slight variation of that. So there's really only kind of one new formula. And this is on your formula sheet. So back here's where we left off. This was your repeated measures ANOVA. Up here on the other side is your independent measures ANOVA. And notice with this line separated off, here's your formulas for your Pearson R. And so I've just indicated the 2 that would be kind of new to this chapter. The other one you could just look straight up above it for sums of squares. So there's 4 things to calculate. First thing we need to calculate is our sums of squares for variable x. Same old sums of squares as you have always had, again, since chapter 4. So this would be the summation of the squared raw scores minus the summation of raw scores squared divided by the number of people is the easiest way to think about it. We don't want to think about that as the number of scores because remember, every one person has been measured twice, once for variable x and once for variable y. So we're not counting every raw score, we're counting every pair of scores. Each person has one pair of scores that goes with them. So you can think about little n as the number of pairs of scores, or you can think about little n as simply the number of people. Either way will get you the correct value there, but don't count every raw score. So this gives me, as we know, some degree of measurement of variability just within variable x all by itself. Are those scores pretty consistent with each other or pretty inconsistent with each other? Then we need to do the same thing for variable y. Oops. And I just noticed writing across, I didn't put my exponent on the back of that. Sorry about that. So it's the same sums of squares formula, just because we're doing it for variable y, take the x's out and put y's in. So again, this is going to give me some amount of measurement of how much chaos there is just in that y variable itself. The scores, again, pretty similar to each other or pretty spread out from each other. It gives us some semblance of that. So these are all old news formulas, nothing new going on there. Next up for us is something we call sums of products. So this is a new symbol, new term, but it's really just another sums of squares. Sums of products gives us a measurement in the end of covariance. This calculation is going to be our numerator. Remember our statistic formulas always follow the same format. What we've always said before is, what are all the differences I observe on the top? And the bottom says, yeah, but how much of that is just random error? What we have now is on the top, what kind of pattern am I observing, am I measuring? And the bottom still says, yeah, but how much of that is chaotic error? So it's still measurement, observation of our data compared to error. And so this is going to be in the top of that. So it's a measure of covariance, products, putting things together. So here's x all by itself. Here's y all by itself. When we put them together, we're going to start to find out in our numerator if they're changing together or if they're changing independently of each other. Well, this formula is, again, just a spin on the other 2. Where for the summation of, or sum of squares for variable x, let's just look at this piece here for a second. Square the raw scores for variable x and then add up all the squared values. Well, how do you square something? You multiply it by itself, right? So we could have written that as sigma xx. This could have looked like this. Those are interchangeable, right? That's just not how we write it in mathematics. We write it like this. But it's the same difference. But now think about what I want to do is put both the variables together. So what I'm going to do is simply remove one of those x's and replace it with a y. Then we look at the back half, and what would we do? We would get the summation of x and multiply it by itself. Well, Now I want the summation of x multiplied by the summation of y. So how does x change all by itself, its independence? How does y change all by itself, its independence? And then how are x and y changing together? How are they connected? So we get our sums of products. So the last thing we need is the actual R statistic itself. So here, it's a pretty straightforward formula. Again, you've got it right on your sheet here. We're just going to take the sums of products in the numerator. And in the denominator, we're going to put our measures of independence. So in the denominator, we're going to get the sums of squares for the x variable multiplied by the sums of squares for the y variable square rooted. So sums of squares x times sums of squares y, almost like squaring, right? And then square rooted and sums of products on the top. And that's it. So remember, I've mentioned this in the slides. I haven't put this in the video quite as explicitly yet. When you calculate this answer, it must be somewhere between 1.00 and positive 1.00. It's got to be somewhere in there. If you are calculating an R statistic, a correlation coefficient, and you do this last calculation and you hit the equal button in your calculator and it tells you the answer is 6.22, it's wrong. It has to be wrong. It can never be any higher than positive 1. It can never be any lower than negative 1. So remember that the farther from 0 you go, either direction, the stronger the pattern is. The farther from 0 you go, it doesn't matter to the right or to the left. Remember, the right's just telling us it's positive direction, and the left is just telling us negative direction. So it's not about good or bad, just like same with t-tests and our z-tests. It's just describing the relationship we're seeing. The closer to 0 we get, like an envelope that looks like a 0, the weaker that pattern is, the weaker that relationship is. So again, it's about your only kind of calculation reality check here. Remember also that sums of squares has to be positive because we're squaring values. So a negative times a negative is a positive. So sums of squares for variable x has to be a positive value. Sums of squares for variable y has to be a positive value. But sums of products does not. That's how we end up with negative r values. If the numerator can be positive or negative, the denominator always has to be positive. So again, if you get an answer that's lower than negative 1 or higher than positive 1, you have absolutely done it wrong. Go back and look at your data again. So when we get done with our calculations from step 3, again, as always, we'll do an example right after we're done with this. We go on to step 4, where, as always, we make a decision. We're either going to reject the null hypothesis or we're going to fail to reject the null hypothesis. If we find our R statistic is in the shaded area, we reject. If it's in the body, we fail to reject. And then the last little thing here is writing these results in APA format is a little bit different than some of the others because it's a different kind of study. We ultimately report this in 3 pieces instead of our usual 2. The first thing we report is the R statistic itself. The next thing we report is the sample size, not degrees of freedom. It's always been degrees of freedom, and you heard me probably just now almost say degrees of freedom again because it's always that, but no, it's the sample size. How many people were in the study? How many pairs of raw scores do you have? And then finally, your actual decision, P either less than or greater than your alpha level. So it's a little bit different in that regard, but it's still the same basic information. What's your calculator say? How many people do you have? What's your decision? So in the next clip, we're going to go ahead and take one of the problems out of the book and grind through it here together.